Hi everyone, welcome back to COP-3402. I'm Brent, just making sure that I'm recording. And today we're going to be going over the basics of file systems. Now, why are we having this lecture? Well, the reason is that many students, their only experience with files is through the graphical user interfaces or GUIs that their systems provide for them. And the problem with using file browsers like this when you're in a system software course that we're in is that it abstracts away and hides the details of how files actually work, which is a problem because files themselves are an abstraction. And so we want to dig into that abstraction and learn more about it, so we're going to be foregoing the use of these file browsers and talking about how files work at a more closer to the machine level. So I said that files were an abstraction, but what does that mean? Well, an abstraction is something that conceals or hides the details of a particular solution to a specific problem and generalizes them to be a solution to a general problem. So some abstractions for lock and key systems are tumbler locks, wafer locks. These are physical lock and key systems. But you can also apply this abstraction of a lock and key to digital systems, so login passwords, cryptographic keys. When you're logging into your computer, the login screen is the key, or the password, I mean, the login screen is the lock, and your password is the key. Now, another abstraction would be for steering wheels. There's the rack and pinion way of implementing a steering wheel, which is a way that's like more physical, analog, I should say. And there's the drive-by-wire mechanism, which uses electrical signals to turn the wheels of a car. There are also abstractions for electrical outlets. So you can think of a diesel generator and a water wheel as both being ways to generate electricity, but they're very different things. So what is the file abstraction? Well, a file captures what's common between different storage hardware. And what different storage hardwares all have in common is that files are ways to read bytes of data and write bytes of data. They are groupings of data, really bytes of data, that we can read and write from. That is what a file is. And we can actually check the contents of a file by using the hex dump utility. So I'm going to make this window smaller, put my terminal on the right here, and I'm going to go to the desktop where I have some files that already exist. I'm going to run hex dump. Actually, first I'm going to cut out the contents of this file, hello.c. You can see it's just a standard hello world program. And if I run hex dump on it without any flags, we just get the hexadecimal contents of that file. Now if I pass the -c flag to this hex dump command, we also get the, I'll make this smaller so you can see it, the ASCII interpreted values of this file as well on the right hand side. The -c stands for canonical, or true way to present the file's contents according to hex dump. There's a shorthand as well, HD, which is hex dump with the -c flag. It's a little bit faster to write. So what about file extensions? So this file here, hello.c, is a .c file. What does that mean? Well, it doesn't really mean much to the computer, to the hardware. It means something to applications and to humans when they're reading these files, just so they can quickly determine what these file types should be. We use file extensions. The saying here is the map is not the territory. This is sort of an older idiom now, but the meaning, to draw it out, or explain it, I suppose, is that if you were to take a map of the United States, let's say, and make the borders of Florida larger and shrink the borders of Texas, for example, the geography of the United States would not change. The physical description of the United States would remain the same. Only the borders, the map that we have drawn, has changed. So the map is not the same thing as the territory itself. Another command that we can use to view the contents or the details of a file is the file command. Now this one's different from other commands we'll be seeing, because file actually looks at the contents of the file and not just its extension to determine what kind of file we're looking at. So if I were to run file on hello.c, it will read the contents of the file and determine that it is C source code ASCII text. If I run it on this MP3 file I have here, beep.mp3, it will say that it's an audio file with ID3 encoding. ID3 is a way of storing metadata about an audio file, like for audio files specifically, the name of the artist, the album name, the year it was released, etc. Now if I were to run copy and copy hello.c to hello.mp3, and if I run let's copy beep.mp3 to beep.c, so copy them to files that have inappropriate extensions, and then run the file command on these inappropriately named files, what do you think will happen? Well, if I run file on hello.mp3, because hello.mp3 really is just C source code, I'll cat it out so you can see what I mean. It's ultimately still C source code because it was copied from a C source file. The contents of, or the output of file will still be C source. It reads the contents of hello.mp3 and can tell that it's still C source. Likewise, if I do file on beep.c, it can tell that it's actually still an mp3 file. But the open command, on the other hand, so now I'm going to use a different command, xdg open, or you can also just use open. Open will open a file in the default application for that file extension. So it's not as sophisticated as file. It doesn't actually look at the contents of the file, but just use the default application for that file. So if I want to try and open the hello.mp3 file, which is really a C file, it will try and open it as an mp3 file. And as you can see, I have a black screen, nothing is happening. That's because hello.mp3 is actually C code. It's inappropriate to use a mp3 viewer for it. Likewise, if I open beep.c, we get just garbled nonsense because beep.c is really an mp3 file and not supposed to edit it directly. But if I open hello.c, we can open a terminal window and actually have it available for editing. And if I were to open beep.mp3, my mp3 player will play the sound stored in this file. And that's correct. So here's some examples of common file types: text files, strings of characters, program files, sequences of binary machine code that your machine actually runs, your CPU runs, and then media files that contain byte sequences and formats that specific applications recognize and can interpret. So how does file actually tell what file each piece of code or a file actually contains? It uses this idea of magic numbers. So magic byte sequences, I should say. So I'm going to open this in a new tab so you can see what I mean. Let me check if it's been opened already here. It was, okay. So here we have the magic number for an audio file with ID3 version 2. And let me run file on beep.mp3 here to see, so I can show you this. Beep.mp3 is an audio file with ID3 version 2.40, which satisfies this on the left-hand side here. Now what the magic number is a sequence of bytes that appear at the start of a file to tell the file command or other programs what kind of file this is. So if I were to run hexdump on beep.mp3 and then pass it, I'm going to pass it to the head command. So this pipe here, this vertical bar operator, tells me to pass whatever is the output of the first command to the second command. So I'm passing the output of hexdump to this this head command to only keep the first 15 lines of the output. And if I do this, you can see that the very first character in this, the very first byte sequence, I suppose, in this MP3 file is 49, 44, 33. And if we look at the interpreted ASCII text of that sequence, it's ID3. And what do you know? According to the actual code stored in the file command itself, that's what this GitHub repo is, the magic byte sequence for audio files with ID3 version 2 metadata is ID3, and we have it here on the right-hand side as well. Similarly, if I were to compile the hello.c file here to a file called hello, so I'm going to do that now, you can see that it's a ELF executable linker file. This is for Linux machines. If I run hexdump on hello and then pipe that to head, you can see the very first characters is the byte sequence.elf, which is the byte sequence, the magic number, so, presumably the magic byte sequence for ELF files. Now, this idea of file extensions not having an impact on file contents can allow us to do something more, allow attackers to do something known as masquerading, where they trick users into thinking of one file of a certain type as another file of a different type, and then run that file on their machine. A famous example of this is the I Love You computer worm. This was released in 2000, and the way this worked was that the creator of this virus, or this worm, had sent out an email to people with an attachment called loveletterforyou.txt.vbs. And Windows machines at the time would hide the .vbs file extension. So a user viewing this attachment would think that it's just loveletterforyou.txt, and they'd be curious to see what the love letter contained. So they would open it and not realize that it was actually a VBS file. A VBS file is a Visual Basic script, so it's actually running code in your machine. And when they ran it, the VBS file would just do what a worm does and open up the user's address book and send out a bunch of emails with the same love letter attachment attached to all of them. A funny fact about this is that the gentleman who made this worm, he's from the Philippines, and at the time the Philippines had no laws. It lacked laws against malware, and so they couldn't prosecute him. They just had to create new laws after the fact and essentially just tell him not to do that again. They couldn't actually prosecute the guy. There's other examples of this. Here you can see this is a more severe attack that actually had more dangerous impacts. And the way this one would work was that it would actually move a TXT file into an exe file. So some more examples of masquerading by using file extensions. And there's another example here that I won't go into in this lecture, but you can view on the website if you're curious. So how do files actually get named? Well, we use directories. So since you've all taken CS1 by this point, you can think of a directory as really a hash table, where we're mapping file names to an internal value called an inode. Now, an inode, well, file systems contain a finite number of inodes, at least on Ubuntu, on my file system. When I configure my file system, when I first configured my file system, when I set up my operating system on my machine, I was given a finite number of inodes, and I can actually check this number by running this command here. Let me make this smaller and show you. dfs or dfs-i. Maybe it's no, df-i. And you can see here on my root directory, I have this many inodes available, I've used this many of them, and I have this many free. So I've used 12% of all my inodes. Every file gets a unique inode. Your operating system assigns a unique inode to each file when it is created. And so for me, if I use all these remaining inodes, I cannot make any more files on my machine. That's just the way that the Unix operating system works. So the true way to identify a file is by its inodes. And that is what a directory sort of does. It maps file names to their inodes. Like I said earlier, it was a hash map. It maps file names, so all the files that are stored in a directory, to their appropriate inodes. So why should we do this, though? Why should we have this level of indirection of mapping file names to inodes? Why can't we just store each file, store each file's name as its name and skip using inodes altogether? Well, there's a few reasons. Really, they come down to performance. Number one, it makes renaming easy. So if I have a table mapping file names to inodes, I can just change the key that a file that a file name inode pair contains to the new file name, and I'm done. I don't have to copy all the file's contents and assign it a new inode number in order to do a rename. And we can also give many names to the same file, so links. And I'm going to give an example of this here. There's a command called ln, which creates links between files. And we can do this because of inodes. There's two different ways to create links. The first way is by just running ln by itself. So if I create a link here, I specify the name of what I want to link to, and then the name of the link itself, b.txt. And if I type in ls, you can see there's a new file here called b.txt. And if I run file on a.txt, and then stat on a.txt to view its inode number, right here, and then stat on b.txt to view its inode number, you'll notice that these two inode numbers are the same. And the analogy you can use to think of this is that creating a link from one file to another is like adding a new gate to your building, to the same building. So if the inode is the building, the links here are different gates to that building on different streets. They have different file names, different streets that those gates are located on, but they link to the same file, the same building ultimately. This also means that if I delete one of these files, rma.txt, and then open b.txt, the contents of the file remain on my system. And if I were to modify, so let me create another link here, b.txt, and I'll call it a.txt, so I'll recreate that a file that I have. If I modify a.txt and change its contents to b, and then cat out the contents of b.txt, we'll see that both files' contents have been updated because they point to the same inode. They have the same, internally they're the same file. Now I'm going to remove b.txt and show you a different kind of file. This is a symbolic link. So I just went over hard links. This is a symbolic link with little s here, a.txt, b.txt. And now if I do ls, you'll see that b.txt is a different color. And if I type in stat b.txt, you can see that it's actually a link. It shows you right here. It's a link to a.txt. And its inode number is actually different from the inode number of a.txt. Oops, stat a.txt. A has this inode number, B has this inode number, so soft links have different inode numbers. What this essentially does is create a whole separate file that lets you go directly into the target file. They're not pointing to the same inode, it's just that whenever you open b.txt, it will essentially, your machine will open a.txt instead. It will redirect you to a.txt. So again, with the analogy I said earlier, if a hard link is like adding another gate to a building, but the gate is on a different street, and soft link is like a teleporter that teleports you directly to that building. So to show you this, if I again open b.txt and change its contents to C, and then cat out the contents of a.txt, the contents of A has changed. But if I were to remove a.txt and then try to cat out the contents of b.txt, I get an error because the file that b.txt links to, or teleports you to in the analogy of the building, is gone. So now if I run ls, you can see that b.txt is actually red to signify that it is a broken link. So if I run stat on b.txt, it tells you. It points to a.txt, but a.txt is gone, so it doesn't work. I'll remove b.txt now. So if you want to learn more about how directories were created or conceived, I recommend reading this paper here, the Unix time-sharing system. It's actually a fairly readable paper, and it introduces some concepts that we sort of take for granted nowadays, like hierarchical file systems. And these might seem like intuitive now, but this was not intuitive at all. I think back in the day, people had to come up with this idea of having a hierarchical file system, and this paper sort of describes it all. It's written by Dennis Ritchie and Ken Thompson, two very famous programmers. Dennis Ritchie invented the C programming language. Ken Thompson invented languages that were that preceded C. Now I'll go back to where I was. Let's see, we were right here. So, sort of what a directory looks like conceptually, the contents of a directory file, is this mapping of names to inode numbers. So how do we move a file? Well, how do we rename a file, I should say? Renaming a file, you would just change this key to a different key. Moving a file, you would just, again, change the key to a different key. It's the same thing. That's why move is the same command for rename on Linux systems. And directories, of course, can contain other directories. So you can have a directory entry that points to another directory, and then you have a hierarchical file system, which is what we've been seeing over this course. Seeing throughout this course, I should say. And I want to kind of just review the file system hierarchy. We have a root directory, which is the /. We can separate nested directories with slashes, so I could say cd bin / or user / bin. All directories contain a dot that points to itself. So if I do, let me actually illustrate this here. I'm going to go to my desktop directory. And if I type in, if I go back to my root actually and say ls - or maybe I should say stat desktop, and we record the inode number 30.360.306.70.905. I'm going to copy this, and I'll create a separate window here and write this down so we can keep a reference to it. If I then go into my desktop directory and type in ls-I, I can see the inode numbers of all the files in my desktop. And if I add the A flag, I can see all the files, even hidden ones, which includes the dot directory. And if we look, the inode number for the dot directory, which again refers to the current directory we're in, the desktop, what do you know? It's the same as the one I had pasted down here. And the dot dot directory references a parent. So again, if I were to run stat dot dot slash, we'll see that the inode is this one. So if I then go into my parent directory, my home directory, and run stat on the dot directory, which is the current directory, we can see that it's the same inode number. So I want to give an example of this now. If I go to a separate window here, I'll close this tab, and you can see I have a system prepared here, or a table and a tree prepared. So I've put black boxes over parts that I'm going to reveal throughout this in the following moments. So let's assume we have a directory user with the following entries. Dot is 1, dot dot is 2, and bin is 3. So if dot is 1, what should the inode value of dot be here? Well, 1, that should be clear. If dot dot is 2, what should the value of dot dot be here? Well, also 2. And dot dot refers to, in this case, let's assume the root directory. 3, of course, if the inode number of bin is 3, then the inode number here is 3. But now things are going to get a little bit trickier. So for the bin directory, if it has a directory entry for the dot directory, that should of course refer to what? 3. Because bin's inode number is 3, and the dot directory refers to the inode number of the current directory, which in this case is bin itself. And what should the inode number of the dot dot directory be? Well, that's the parent. The parent of bin is user. User is an inode number of 1, so 1. And then if LS's inode number is 4, then of course this would be 4. Now there's two different kinds of paths. We reviewed this earlier, but I'll just review it again to be complete. There's absolute paths, which start with a / from the root of your file system hierarchy. So if I were to, let me close this here so I can show you an example. If I were to do cd/, it would take me immediately to the root of my file system. And I could say cd/home bpapis desktop, and that would take me to my desktop. But there's also relative paths. So if I were to go back here to my home directory, that's what the tilde stands for. You can see if I do pwd to see my current directory, I'm really just in home bpapis. And I cd into, if I just type in desktop, well, this is going to be a relative directory relative to my current directory. So my full path is now /home/bpapis/desktop. That's the same path I had used earlier when I typed in a full path. The working directory, that's whatever directory is your current directory. You can always access this via pwd. You can always check it. The parent directory, we had seen that. That's //. And now just to give a quick view of one command line tool that'll be very useful for looking at inode numbers, it's going to be the -i flag, like I said earlier. If you want to see these one line at a time, which is a little bit easier to see sometimes, you can pass the -1 flag to ls, and now you get each file on its separate line. And you'll notice that the dot and dot dot directories are missing. That's because ls does not display them by default. To show them, you just have to pass the a flag to ls, and we can combine this with I and 1 so that we get, oops, let me go back to the desktop and do this again, with ai and 1, so you can view all the inodes in the current directory, including dot and dot dot. So there's other ways you can use files, network sockets, pipes. For example, we saw earlier this pipe command, so I said hd hello.c, or let's just say hello, and then I piped it to head. This piped the output of hello, which is a byte sequence, to the input of the head command. and head would then read it and then print out the first 15 lines or so of input. There's also random number generations. You can actually check this out yourself. If you cat out the contents of let me actually quit this here, cat/dev urandom, you'll get a bunch of garbled nonsense. I'm going to exit it now. That's because this is supposed to be interpreted as a byte sequence, and it's all random, which is pretty cool. So if I do hex dump or HD, really just hex dump I'll say, you'll see I get a bunch of random numbers from dev random. And what you can really do to make this useful is actually pipe this to head, and that way it's not just an endless sequence of random numbers, you get like a snapshot of randomness every time you run this command. You can see it's always different. There's also dev null. So dev null is sort of like no man's land in your machine. Anything that goes to dev null is gone. So what I can do is cat the contents of hello.c to view it. But as we had shown earlier in this course, you can use redirects to redirect the output of one command to another file. So I can redirect the output of catting hello.c to the console to dev null, and what will happen is nothing gets printed. That's because the output is being redirected to this trash bin, essentially, of a file. You can actually write directly to RAM by writing to dev mem. I don't recommend doing this unless you know what you're doing. Kernel settings information in proc, graphics, so actually some applications write directly to your graphics cards and graphics parts of your machine, graphics processors, to display pixels on your screen. I recommend not doing this again unless you know what you're doing. Peripherals, temperature sensors, and other measurement devices. What's kind of cool is that on Linux, this is different from Windows, because on Windows, if you were to plug in a flash drive onto your machine, you'll get a new drive, or a new SSD on your machine, you'll get a new drive. Like by default on Windows, you have a C drive, but if you plug in, let's say, solid state drive, you might get a D drive or an E drive. But on Linux, this will appear in the media directory here. So I have media, bpapis, and then actually in here, if I were to plug in a flash drive on my machine, it would be a part of my file hierarchy. It wouldn't be a new root. There's only one root on Linux. And there's other topics we can talk about as well, but these are reserved for an operating systems class. So I recommend, if you're interested in these, check out a book on all these different topics. One that I would strongly recommend is this one, Operating Systems in 3 Easy Pieces. It's totally free. It's actually fun to read. The writer has a bit of a fun tone in his writing. It's actually a married couple who wrote this book, and they have a very nice tone when they write. It's fun to read. It's pretty straightforward. It's not overly complex. It's not dry. So I recommend reading this book if you want to learn more about operating systems. And just to reiterate the key takeaways of this lecture, a file is an abstraction. It's not the actual byte sequences on your machine. It's just an abstraction for reading and writing byte sequences, reading and writing bytes from a sequence. File hierarchies, they work by having a directory, which has directory entries which may contain other directories. Referring to files with paths, there's absolute paths and relative paths. Absolute paths begin with a / signifying the root directory of your machine. Relative paths do not begin with a / and are relative to the current working directory, which you can always access with the pwd command. So that concludes this lecture, and I'll see you all on Thursday.